This is the third and final part of a three-part video on problems and solutions in indeterminate forms and L'Hopital's rule. Problems 1 through 15 were discussed in parts 1 and 2, and so in this video we start with problem 16. I won't be talking about the background on indeterminate forms and L'Hopital rule, and that's because I have a separate two-part video on these topics that you can check out if you need to. The links are in the video description. Here's problem 16, where we are trying to find, we are interested in finding x raised to the power 3x as x goes to 0 from the right, which means x is bigger than 0. When x goes to 0, we have a situation where 0 is raised to the power 0, and that's an indeterminate form of the power type. In order to use L'Hopital's rule, we first have to change this to a quotient indeterminate form, and the standard procedure is to use the logarithm to move the power from where it is to the side, and that procedure gives us a new power form like this. And as soon as we figure out this limit, e to that number, whatever it is, will be the limit of x to the 3x. Notice that as x goes to 0, natural log of x goes to minus infinity, and that's something you can quickly check, maybe with a computer, by drawing a graph. The limit of x times log 3x is 0. That's something we showed in problem 10 as an example of 0 times infinity product form. And so 3 times that, of course, will also be 0, and that gives us the power of e here. And so the answer is e to the 0 or 1. It's worth mentioning that there is nothing special about the number 3. If I use any number c here instead of 3, the whole thing works out the same way, and we have the same answer, 1. In problem 16, we saw that the limit of an expression of 0 over 0 type could be 1. But of course, it turns out that 0 to the 0 is indeterminate form, and in fact it can have an infinity of real numbers as possible limits. Let's see how that can happen in a single example. Consider the limit of this power, where in the exponent I have a c. This c is any real number, any fixed real number, which we think of as a constant. As x goes to infinity, this inside the parentheses goes to 0. 1 over x plus 1 goes to 0. Natural log of x goes to infinity, which means that constant over infinity will be 0. So we have a 0 to the power 0 expression. Let's use the standard procedure to write this limit as e raised to this limit. Let's take a look at this fraction inside the limit and simplify it. Here it is. I'll rewrite ln of 1 over x plus 1 as negative ln of x plus 1, because that's the same thing as ln of x plus 1 to the negative 1, which is what 1 over x plus 1 is. And so we end up with this expression. Now, that the last fraction over here, as x goes to infinity, ln of x plus 1 goes to infinity, ln of x goes to infinity. So we have an infinity over infinity quotient indeterminate form, and we can apply L'Hopital's rule. Derivative of the numerator is 1 over x plus 1. The denominator is 1 over x. I can rewrite this fraction more simply this way. But notice that as x goes to infinity, I still come up with an infinity over infinity expression. So I apply L'Hopital's rule once more. The derivative of x is 1. Derivative of x plus 1 is 1. So the limit comes out 1. And then, of course, we incorporate that over here. We get minus c times 1, and that is just minus c. And that means limit that we have here in the exponent is minus c, and the answer therefore is e to the minus c. And depending on the specific value of c, this e to the minus c can be any positive real number. And therefore, we have an infinity of possible values. In problem 18, we take a look at this limit, x plus 1 to the 1 over x as x goes to infinity. Notice that as x goes to infinity, inside the parentheses goes to infinity, while 1 over x goes to 0. So we have a indeterminate form, the infinity to the 0. We use the standard procedure with the logarithm to change this fraction to e to some limit that you see here. And here I've just written 1 over x times ln of x plus 1 as ln of x plus 1 divided by x. Now we calculate this limit. The fraction here, ln of x plus 1 over x, is an infinity over infinity form, which is something we can apply L'Hopital's rule to. Derivative of ln of x plus 1 is 1 over x plus 1. Derivative of x is 1. And if I write this up in the simpler form, notice that as x goes to infinity, the denominator blows up and 1 over that goes to 0. And since that's this limit over here, this is 0, which means that the answer is e to the 0 or 1. In problem 19, we look at this limit here, which turns out to be a 1 to the infinity indeterminate form. That's because as x goes to 0 plus 1 over x goes to infinity, and of course x plus 1 goes to 1. We convert this to a quotient indeterminate form using the logarithm in the usual way. We get 1 over x times natural log of x plus 1, which I can write more neatly in this form. And now our objective is to figure out what this limit is. Ln of x plus 1 over x as x goes to 0 is something that goes to 0 over 0 because natural log of 1 is 0. And so we apply L'Hopital's rule to this. We get derivative of ln is 1 over x plus 1. Derivative of x is 1. Write that up is 1 over x plus 1. And as x goes to 0, it drops out, and we get 1 for the limit. If I put that back in here, I'll get e to the 1, or e, as the answer to the limit. Couple of things worth mentioning with regard to this problem is if I replace 1 over x with c over x, where c is any real number, I'll get the same answer, same calculation, same answer. And secondly, this limit has a more common form as something goes to infinity rather 0. Let me explain. because that's kind of interesting, and you see it more often in textbooks as well as in applications. Let's make a substitution: c over x, for call that u, and then notice that as x goes to 0, c over x, or u, goes to infinity. Actually, it goes to plus infinity if c is positive, and it goes to minus infinity if c is negative. So we have these two special cases. First, but it is immaterial as far as calculations are concerned. Secondly, if u is c over x, then x is c over u, so we can make some substitutions in the original expression. X becomes c over u, 1 was itself, and c over x is u, and so the whole thing comes out e to the c. As special cases, if c is equal to -1, we get the answer e to the -1, which is 1 over e. And if c happens to be 1/2, then we get a square root of e to the 1/2 for answer in these special cases. In problem 20, we look at the limit as x goes to 0 of cosine x to the power 1 over x squared. As x goes to 0, cosine of x goes to cosine of 0, which is equal to 1. 1 over x goes to infinity, so we end up with 1 to the power infinity indeterminate form. We changed that using a standard procedure to with a logarithm to something like this. Now, in the numerator, inside the limit, as x goes to 0, natural log of cosine of x goes to natural log of 1, since cosine of 0 is 1, and natural log of 1 is 0. So here's the power that I've rewritten here. So we get the top goes to 0, the bottom goes to 0. That's a 0 over 0 quotient indeterminate form. We can apply L'Hopital's rule. If I take the derivative of ln of cosine of x using the chain rule, we get the derivative of ln of cosine of x, 1 over cosine of x, times the derivative of cosine of x minus sine of x. Derivative of x squared is 2x. I'll bring the cosine of x down below and rewrite the fraction in this fashion. As x goes to 0, sine of x goes to 0. And down here, x goes to 0, so the denominator goes to 0 as well. And we once again get a 0 over 0 indeterminate form. We use L'Hopital's rule again. Derivative of the numerator is minus sine x is minus cosine of x. In the denominator, we use the product rule. Derivative of the first function, 2x is 2, times the second function, cosine of x, plus the derivative of cosine of x minus sine x times 2x. And at this stage, notice that if I set x equal to 0, I get cosine of 0 in the numerator, that's 1. Likewise down here, and x is 0, so this whole term drops to 0. And so what's left is minus 1 over 2 minus 1/2. And if this limit is 1/2, the limit that we are looking for is e to the minus 1/2, or 1 over a square root of e. In this last problem, I'll point out a occasional failure of L'Hopital's rule, which happens when we have a fraction. We start with a fraction that actually has a limit. It may be 0 over 0 or infinity over infinity. But when we take the derivatives, f prime divided by g prime, and take the limit of that, that limit does not exist. Obviously, then L'Hopital's rule cannot be applied, and we must use a different method to figure out the limit of the original fraction. And so here's an example of that. As limit as x goes to infinity of this fraction goes to infinity over infinity. That's because sine of x is stuck between -1 and 1. And if I subtract that number from an infinitely large number, I still get infinity. Now, because this is infinity over infinity, we can go ahead and apply L'Hopital's rule. Derivative of x is 1. Derivative of x is 1. Derivative of sine x is cosine x. And so we get this. But as x goes to infinity, this expression has no limit, because cosine of x is stuck between -1 and 1, and it oscillates, it never settles down into any number, and 1 minus that also never settles down to any number. So this limit does not exist. L'Hopital's rule doesn't give a limit, but when we encounter a situation like that, we ought to go back to the original fraction and see if there is some other way of finding its limit. And in this case, it's easy to figure that out. If I get the original fraction and break it into two fractions, x over x minus sine x over x, I'll get x over x equals 1 minus sine x over x. Because sine x is stuck between -1 and 1, and as x goes to infinity, that number over infinity will drop down to 0, and I'm left with 1. And that is the correct answer to this problem. Well, this is a good place to stop, and I'll invite you to look at some of the other videos on L'Hopital's rule and indeterminate forms that I have in the video description.